Good evening, and welcome to this Texas Instruments Australia webinar. Tonight's focus is on the new calculus content in the revised VCE Mathematics Study Design. My name is Emily, and I'll be your host for this evening. Our presenter tonight is Roger Wander. Roger is a very experienced secondary mathematics teacher who has taught in the classroom for over 30 years. More recently, he has taken on a role of supporting the training of teachers through the University of Melbourne, as well as with presenting numerous workshops, including many for Texas Instruments. Roger has a particular interest and skill in writing classroom activities, and he has been kind enough to supply one based on the content of tonight's webinar, which you will all receive access to after the event. As we have a very full session tonight, we also have Peter Flynn joining us to help answer any of your questions. You might recognise Peter's name from having presented a couple of our specialist webinars recently. He is currently an educational technology consultant with TI Australia and has also been involved in mathematics education for over 30 years. So you're all in very experienced hands tonight.
Thank you, Emily. And hello, everyone. Okay, we're going to begin tonight with a little PowerPoint, and we will go occasionally over to the TI-Nspire software. So, new calculus content for 2023. Two different editions have come into the study design. The central difference method and the trapezium method for approximating areas. So central difference is for approximating gradient. And in both cases, the approximation techniques are ones that have come into the course. Here we've got some information about where we would find these changes in the study design. Unit 2 of Maths Methods is where we find the information about the central difference approximation in the various outcomes and key knowledge, and then a statement of what the central difference approximation is in the area of study 3, calculus. For 3 and 4, the approximation of definite integrals using the Trapezium Rule is referred to in outcome 1, in the area of study calculus, and outcome 1 key knowledge, and in the key skills. So students will definitely need to be able to use these. I'm conscious of the fact that after a webinar and you have this information, and there will be some teachers out there who perhaps will find in 2023 that they're teaching Maths Methods for the first time, and others who have just been teaching it for a little while, such as the staffing situation in our schools at the present time. So to support this, we have a Word document on the website. Now, it's not up there now, but apparently it's going to be there very soon. It's a student activity Word document that's got some theory, some by hand and Nspire CAS explanations, and some open questions. I'll just show you what that looks like. It's about a 9 or 10 page document. This is the student activity sheet. And in this, students will be able to go through some of the things that we're going through tonight. With your support, by following some of the instructions, etc., you will be able to help those students get a better handle on these two very important approximations that they need to learn. There's a teacher version of the student activity as well, and that has the full set of answers and some teaching suggestions that I've written that may help you. We also have Nspire files, which will be present on the website, and those files will be the ones that I add to tonight, and whatever we finish with will be saved and will be up on the website for you to access. Okay, we start with the central difference approximation. Well, what is it? It's a way of estimating what the gradient of the tangent line is. And students coming out of year 10 certainly will know that you can't have a gradient unless you have 2 points. And if they know something about tangent lines, there'll be a disconnect in their knowledge. So certainly taking a look at this particular approximation technique, which says that if you want to get an estimate of the gradient of the tangent to the function y equals f of x at point P, where the first coordinate is, say, A, that you just go to the right and left of that point by the same horizontal distance. And I would ask teachers to just take note of that if that's above the value of A on the x-axis, then the point L for left is B units to the left, and this point, which is under point R, is B units to the right. So we have A minus B and A plus B. That's really important. The whole technique involves the fact that, well, if we make that distance, the B distance shorter, the smaller and smaller we make B, the closer and closer this secant line, the blue line, becomes to the tangent line. And that's the whole purpose of the exercise. In the student worksheet, I think there's no getting around the fact that substitution by hand, working out a few things with maybe some technology support, but a lot of this can be done by students in their heads. Filling out a table manually rather than doing it all electronically is a good idea. So you'll see this table here. I've chosen a function that's more relevant probably to year 12, to units 3 and 4, but the same kind of procedure where the A value is given as 2, and the B value, you fill out values for when B is equal to 1, and then check out what happens when B is equal to 0.5. And you get these values changing depending on what the function value is. Now, how are we going to use Nspire for all of this? Well, there are a couple different ways. And the first way that I thought would be to use a notes page, which we'll be going to in just a minute. And just keeping in mind that the notes page is a feature of Nspire that really allows us to do some wonderful instant updating, changing values. Apologies for the triple P on the approximation. There's a spelling error there. Must have got carried away. But when you are doing these approximations, you're not going to want to stay with the same function all the time, and you can really update the function and the various parameters for A and B. So we're going to take a look at one of those files now. So I'll just revert to this first file, which, as I said, will be on the website. It's referred to as CDA1. And I've started to fill out the notes page using Control M to generate what's called a math box. And just to save time here, I've put the first 3 in already. Just a little explanation. The function is brackets x minus 2, close brackets, multiplied by the square root of x plus 1. That's stored as f of x. The number 2 is stored as the value A, and the value 1 is stored as the value for B. So in other words, we're going to find an approximation for the gradient of the tangent line to this curve, the curve of function f, at the point where A is equal to 2, and we're going to start out with a B value, remember going either side, left and right of A, with a B value of 1. Now what I've left here is we're going to complete the math box that's here. So those of you who have never used a maths page before can get a little bit of practice at doing that. So the numerator is f of A plus B. That's the value of the right boundary of that triangle that I had up on screen earlier. We subtract from that the value of f, open brackets, A minus B. For those really new to Nspire, you might notice that some of these are in bold, and that's because they've been defined. Up here, as soon as I assigned that rule to function f, f was emboldened. It's referred to as a function variable. A and B are numerical variables. And so a lot of this is in bold. I didn't go to any kind of formatting of that. It just does that automatically. And it's Nspire's way of reminding you that you have some stored variables. Now, we want to store that whole function or that whole fraction as the gradient of the secant. I'm going to press the right button once to move the cursor to the right and move it right again. Now it's still, the cursor is in the text, in the math box. You possibly can't see it as that, but it's when it's in that position that we're ready to store this variable. We store by pressing Control var. You see above the var key is a blue STO. That generates that arrow, and we're going to refer to that as seek underscore, and the underscore on the handheld is found here by going to, I'm doing it best here on the computer keyboard. Seek underscore grad. We have to, when you're defining variables, for those who don't know, you can't put in spaces. You've got to put in some sort of symbol. So that stands for secant gradient, the gradient of that secant line. When I press enter, the value of that gradient will have been calculated. And you see it's in blue, but bold. And the value is exactly root 2 plus 2 over 2. And that'll be one of the values that's generated on that table that you saw back in one of the earlier slides. Now, because that is a stored variable value, I'm going to now open up a calculator page because I want to store a few of these values. So one way to do that is to press Dock, scroll down to Insert. We're going to insert a calculator page. So this will become page 1.2. I'm going to just press the var key to see that, yes, we do have those three variables. The first two are numerical. The second one is a function variable. And the other one, seek gradient, has been generated by the notes page. So that's the one that I want to access rather than typing it in again. And if I want to see what value I've got, I press enter and I'll still get that exact value. But if I want to see the decimal value, and that'll be important for the next step, I'm going to press Control enter, and I get the decimal value, and I've got mine going out to a zillion decimal places, so 1.707 approximately. Okay, well, let's navigate back to page 1.1, and let's say, well, suppose we want to make the value of b smaller. I go back to the math box that b is in, and I move my cursor just to the left here, so that I'm going to I'll edit this one. I'll do the backspace so it's ready to put another number in, and let's call it 0.5 instead. Now, as soon as I enter 0.5, I've introduced a decimal. It will not give me, when I press the enter for this, it's going to update the secant gradient, but it will not give it as that exact value. It'll give me it as a decimal value. So I'll press enter, and there it is, close to what we had before, but it's a little bit different. And geometrically, we would see that same thing if we did something similar to what you saw on one of those slides. If I now navigate to the calculator, page 1.2, and press the up arrow twice, twice, and press enter for the automatic copying down that you probably value quite a bit. I know I do on the calculator page. It will now pick up, or it should pick up, the latest value for secant gradient. Previously, it was that root 2 plus 2 over 2. Now when I press enter, it's going to give me the updated value. And I've got a record now of what's happened. I can't see, I have to have remembered that the first one was generated for b equals 1. The second one was generated for b equals 0.5. And I'm going to do it one more time for an even smaller value of b. Let's make b equal to 0.25. Now, there's no magic about which ones you choose in what I'm doing tonight, but you may find that those of you teachers who write your own materials, or if you're using textbooks where you have examples and you start to see some suggested materials from other people, that some questions will specify what the values of b are going to be, and others will tease it out a little bit more and say, for appropriately smaller values of b. It all depends on the wording of the question. Now, when I press enter, I don't have to have the cursor to do the updating. I don't have to have the cursor to the very right. I can just press enter and we watch things change. Now, we're getting a value of b, or sorry, for the secant gradient, that now is 1.73 something. To see it on the calculator page, I'll go over to 1.2, press up twice to grab that variable, press enter to copy it down, press enter again, and I've got this record now. And some of you might smell a gigantic rat here and say, that looks suspiciously like the square root of 3. Well, surprise, surprise, when you do your calculus on this function, you will find that the exact value of the gradient of this curve, y equals f of x, when x is equal to 2, the gradient is exactly the square root of 3. So it's a really nice numerical approach to that particular limit. Okay, let's go back to the slides here. And remember, you will have an opportunity to be asking questions at the end, to be posting them online, and Peter Flynn will answer a few, and I will answer a few as well. So let's see where we were here. Okay. And now we go to this slide. So put that up on full screen for you. There's also a way to do the central difference approximation by using spreadsheets. And I found that it's easier to have a calculator page and then list in spreadsheets. And so I'm going to be creating or adding to something that I prepared earlier, which will have that kind of look. So when you download the PowerPoint that we're using tonight, because you will be able to do that, you'll be able to see these in more detail and spend a little bit more time than possibly we have this evening. Okay, so to do that, I'm going to go back to my Nspire file. We were looking at this file, CDA1. You notice we were on page 1.2. That was a calculator page. I'm going to navigate over to problem 2.1. Now, for those, again, not used to Nspire, or for those who have not used it very much, the advantage of having a completely different problem is that all the variables from the past work are forgotten. And sometimes that's a really good thing, because you can start to use the same letters time and time again, and you're trying to figure out which one's which. So I'm going to go to, I started a calculator page 2.1. This word define, you get under menu actions, you'll find define, or you can just type in define and press the space bar. And I've defined the function f of x to be equal to the same one that we had before. And notice that the storing of the variable is done in the same way, except it's you don't have a math box to put in here. So, so this is just on a calculator page, so it's slightly different. Okay, well, Notice that I haven't stored a value of b. There was a reason for doing that because I wanted b to change in my spreadsheet as I went along. So let's go to the next page, which is 2.2. I've set that up as a partially completed spreadsheet, and you notice that I've gone a little bit silly here, and column A, I'm calling B, but because oftentimes the software wants you to differentiate between a letter as a column name or a letter as a variable, I thought that I could make things a little bit easier by just calling it B. So we're buzzing around here, and I've manually entered these values 1, and I called it 1 point because I wanted all these answers to be decimals, none of them to involve exact quantities. So 1 point or 1.0, 0.5, and 0.25 as we did before. Now, for this column, which I've called the variable left bound, that's defined as f of a minus b. That's the left boundary of that triangle that we saw earlier. I'm about to complete the right boundary here, and I've called it f brackets a plus b, so it's the function value of 2 plus 1. Down here, it'll be the function value of 2 plus 0.5, and here the function value of 2 plus 0.25. Now, when I press enter, it's going to have a problem with this because it doesn't know what I mean by A. It's asking column or variable. Those of you who have not used the spreadsheet before here haven't seen this before, but many of you have, I realize. But for those who haven't, I'm taking a little bit of time to do this. So we want it to refer to the variable A, not to column A. So I click on this button, I choose, then go down one and choose for variable reference. I click OK, and then those values have come up. And those are just the y coordinates of the function at f of 1, sorry, f of 2, f of 3, because 2 plus 1, f of 2.5, f of 2.25. But it's done it instantly for us. Okay, now for the secant gradient, I'm going to press equals to start off the formula. And I'm going to do all my editing down here rather than up here because very soon the listen spreadsheet cells get a bit cramped. And the secant gradient is going to be a fraction, so I'll access Control Divide. And up here, I want f of a plus b, but that's just the variable r bound. So I can make things a lot easier for myself if I choose r bound from my list of variables. If I go up here and press var, oh, I guess I'm going to have to type it in. So up here in this box, I'm going to start off with r bound, R-B-O-U-N-D, so the right boundary, minus the left boundary, which is L bound. I probably could have clicked on that, on those cells, but typing it in isn't so bad. And because it's bold, it's guaranteed that we've got the right workings there. Down below, we have 2 times b. So I'm going to put 2 times, just to make sure. And remember, the variable is not just the straight letter b, it's B-double-E. And now it's going to access that number. When I press enter, then I've got my 3 values that I saw before, but it's all recorded at once. And the advantage here is that you can see the b value for which that gradient is associated. And that's very, very strong. There's nothing preventing you from entering another value of b, and instantly these would be updated as well. I'm not going to do that now, but you can see that as b gets close to 0, this value is approaching 1.732 something, which I think is the accepted value for the square root of 3. Okay, So we'll go back to the PowerPoint. You will have time to take a look at these later, of course, at the end of the webinar, and certainly afterwards by accessing the materials that will be up on the website. So let's go back to the PowerPoint at that slide. And we'll continue on now, taking a look at a second approximation, the one that is in the study design appears for Maths Methods 3 and 4, and that is the approximation for the area under a curve. And one of the first things that happens in the student activity that I've written to accompany all of this is just getting students used to, for those who haven't seen this before or possibly aren't aware, that not every trapezium has its parallel sides horizontal. A lot of textbooks, I must say, present them only that way, and it's convenient to put them into worksheets. I understand all of that, but in these cases here, we have to get used to our trapezia that we are dealing with having vertical sides. So once again, I've got a particular function designated as y equals f of x. And this time, a and b are standing for the left and right boundaries of the particular area. I'm certainly teasing out the fact that, this exact area here is fine until you get to this bit, and we don't have a formula when we have a curved edge there. So we have to resort to the geometry that we do know, which is areas of trapezia. That's what we are doing. In previous years, it's been areas of left and right rectangles, but now we're looking at trapezia. In the study of geometry back in year 8 and year 9, students will remember the formula involving something about 1/2 the height times a plus b. And it's important to get that out of students' heads pretty quickly, because in this case, if they want to be doing this kind of work, and oftentimes the values will be given as a and b. A and b are just referring to the x coordinates of the left and right boundaries. We talk about the width rather than the height of the trapezium. It fulfills the same function in the formula, but I'll talk about that as the width because it's a horizontal distance, b minus a. When there's only one width and only one trapezium, even that gives you a pretty good approximation for this particular curve, because there's not that much of a gap between the actual function graph and that black line which forms the fourth side of the trapezium. But when you start to break this up into a multitude of trapezia, you get an even better approximation. So once again, this limiting idea takes place. And notice the diagram on the right, where you have A and B chopped up into 3 equal divisions, and it's really important that they're equal. So the width of each of these trapezia is 1/3 of what it used to be, but the calculations involve getting the lengths of the 2 vertical sides, multiplying by the width and dividing by 2, because you've got the average of the 2 vertical sides. Okay. Notice that for some functions, the trapezia will overestimate, and you'll have the top side that's replacing the curved side actually being above the curve. And so that's going to happen when it minimizes and starts to come back up. So just a reminder to teachers to select the examples carefully. I think it's always of interest to be able to have one of each type. And the one that I'm focusing on today for our work with Nspire will be this parabola, this quadratic function y equals f of x, where f of x is equal to x minus 3, all in brackets squared, plus 2. Okay. So let's take a look at what we can do. Before we use the notes aspect of Nspire, a little bit of preparing the students who have never seen the summation formula before, I thought was good. And honestly, that might also be something that's quite beneficial to a number of teachers, particularly those of you who possibly find yourself teaching methods next year for the very first time. Now, this is another completely different example. It's an inverted parabola graph, obviously. And between A and B, which are still 1 and 4, I've divided it up into 6 rectangles, six trapezia rather than 3, and then used Nspire's ability to find each of their area measures and to do the set them out as individual polygons and color them differently. We don't tonight, I believe, have time to get into too much of how to do these drawings, but if there is time, I certainly will run through a little bit of that using the geometry aspect of the graphs menu. What I'm attempting to do here is to show that for any particular trapezium, and I've highlighted the third trapezium, the parallel sides, the left boundary, is x, or is the a value, which is this first dot. I have not labeled it in this diagram. It is over here, but it's not over here. It's a plus 2 lots of the width. The right boundary is a plus 3 lots of the width. And aligning the coefficient of w in this expression and in this expression, aligning that with the number of the trapezium gives us a clue as to how we can set up this summation formula. The third trapezium uses 2w for the left boundary and 3w for the right boundary. If I had chosen to talk about the yellow one instead, which is the fifth trapezium, the fifth trapezium uses the fourth boundary, this line, which is a plus 4w, and it uses also the height of this boundary, which is a plus 5w. That's for the fifth one. So getting the connection between the number of the trapezium and the coefficient of the values here in the left boundary and the right boundary is going to be essential. This particular area would be 1/2 times the width, which in this case also happens to be 1/2, multiplied by the sum of the two boundary heights, which are a plus 2w and a plus 3w. Now, knowing that helps us to understand how the trapezium rule could again be use the notes pages of Nspire to find out all these various values. So just have a look at what we're about to do, and I'm going to now go to a notes page, paying particular attention to the summation formula, which will talk about going from the first trapezium to the nth trapezium. 1/2 times the width. The 1/2 is because of the averaging aspect. W, you could have W times 1/2 if you wanted to do that, it wouldn't matter. And then here's, and it's multiplied then by F of A plus I minus 1 times W plus F of A plus IW. So that's like if I was equal to 3, then it would be looking at the A plus F of A plus 2W plus F of A plus 3W, but it will do that automatically, and it will add up all of them instantly. And this becomes then a very powerful way of accessing, of using Nspire here. So let's go to our second Nspire file, which I've entitled Area Trap 1. It's not, doesn't have anything completed in here, so we'll have a chance to see how the math box is created. I'm just going to get a couple of things together here. So when we have to access a math box, press Control M. Whoops, you have to hold down Control M, and a little box like that appears. And in the first one of these, we're going to put in the function rule, just the brackets. This is that right side up parabola, brackets x minus 3, close brackets, squared, plus 2. We're going to store that as f of x. So remember, store is control var, and then f open brackets x. Remember, there's no danger. It's a brand new file, so we don't have to worry about any overlapping from what we've done before. When we press enter, it indicates that it's done. Press enter again, and we have a chance now to put in another math box. So once again, Control M. So we've got our function located now. Now we're going to put the initial a value. Remember, that's the left bound. So we'll store that. In this case, we're saying that it's 2. So we're going to store that. Control var, store that as a. Press enter and press enter again. For the next value we're going to put in is we're going to put an initial width of 1. We're going to say, well, let's have our trapezia have a width of 1. We will be able to change that shortly. So when that trapezium width is 1, we're going to store that, Control var, store that as variable w, press enter, do that again for Control M, and we're going to store 4 as the variable for b. Remember, b is taking on a different role in this approximation than it did in central difference. Here, b is the very far right side of the required area. So a and b, we're going from 2 to 4. Actually, I'd like to make that 1 to 4, because I think that's what we had originally. So let's just go back up there. You can see how easy it is to change these. We're going from 1 to 4, from a to b, with a width of 1. And now that we have this, we're going to put in our formula, which will automatically calculate the number of trapezia that we have. And you might remember this from before. First, I'll do Control M for another math box, and we're going to put in the fraction. So Control divide. B minus A, see those showing up as bold again. Divide that by the width, which we have already, and we're going to then store that. I go to the right, so it's right at the edge of the math box there. Now I can press Control, store, and we're going to store that as n, which will stand for the number of trapezia. This is really important. Press enter, and we've got that, and you can see it's done a calculation for us. Okay. Well, now the major formula that we want to enter in, and the one that takes the most time, but the big relief is once you enter it once, and if you save this page, you can use it all the time because it doesn't change. So we want to access the summation formula. I'm going to press Control M to put in another math box, and now going to the template key, which is here just to the right of the 9. I will enter this is highlighted because I've been using it so many times, the Greek sigma letter, and fortunately it's nice and big. It's much bigger than you were possibly expecting, but that's good because there's a lot to fit in here. The first thing in the summation formula is that we have our counter, which says that I will go from 1 up to n. You don't want to put in the number, you want to put in n because we want to be able to update this and have this stay current. So I is equal to from 1 to n, and what's it going to add up? It's going to add up all these trapezium areas. To do that, we're going to put in the fraction 1/2. I'm going to put it in the order that I had it in before to maintain consistency. So control divide for the fraction 1/2, and then making sure that I put a multiplication sign just in case. There's sometimes when you do need it and sometimes you don't. Remember, it's going to be half the width. I press W and it's going to pick up whatever value of W I have in there, and that can change as well. That will be multiplied by the sum of the two function values. So be ready for brackets here, folks. We have an open bracket, and we're going to have our first function value be our right boundary, which is f of, or sorry, I'll do the left boundary. The order doesn't matter because they're going to be added. Function of, remember a plus 2w and a plus 3w? Well, this is going to be a plus brackets I minus 1 close brackets times w. And I better actually put in that bracket, even though it's grayed and therefore it's ghosted for us. And then plus the other function value, which is f. And this is my right boundary of the trapezium, f open brackets a plus just I times w. Close the brackets. And then when I press enter, I should get the area of all three. How do I know it's 3? Because n's value currently was 3. We'll get all of those trapezia added up, and it's 19/2 or 9.5. Well, that's if that area, and it's probably worth going back to the PowerPoint just to see what I was talking about here. This is this question. The area of this trapezium is 9.5 square units. Okay, its width is equal to 1. There's its height, there's its height. We found the average of those, etc. Sorry, that wasn't the only one. It was this one, and this one added up to a total of 9.5. Pardon me. Okay, so what happens if I want to make the width something different from 1? Say if I want to make the width equal to 0.5. If I want to make the width equal to 0.5, we should get a lot of changes. And the first thing should be that now the n value will be b minus a, which is 3, divided by 0.5. It should be 6. When I press enter, there it is. And more importantly, my area sum has changed now to a decimal, 9.125. Smaller than the 9.5 that we got earlier, and rightfully smaller because this was an overestimation, and we should be finding as the trapezia get thinner and thinner, we should be finding that the estimate is getting closer and closer to the actual value. for those who have already applied their calculus knowledge, the actual area enclosed is exactly 9. So the more we change, I'll just do this one more time here, change that maybe to 0.25 for W. We now have 12 trapezia, and it's even closer to 9. So you can make it as small as you want. The only disadvantage here is that, once again, we have not kept a record of what's what. You could put in a calculator page and keep these values. I didn't store this as anything. I could have stored it again as a trap area, trap underscore area, and then had a record as I showed before. It's up to you what you want to do, and it will all depend on what the question that the students are answering is going to be doing. Okay, well, I'm going to go back to the PowerPoint and finish up here because we're just about out of time. But I know that for some of you, the question is, well, that's fine for all these calculations, but gee, I'd like to be able to do some of these drawings. It does take a while to do the drawings, and at the conclusion of the student activity sheet, and the teacher version as well, I've given a little bit of a contact information if you want to learn more about forming those diagrams, because they really are fun to do, and they can be really good teaching devices. So that's as far as we got there. Here's something I didn't get to tonight, but you can set up a spreadsheet in the same way that I did before, where you have the values of the left bound. I think I put those in manually, I can't remember. And then the right bound, the trapezium area, and then this last column for the sum total. And that becomes a really interesting exercise as well. So it requires a calculator page ahead of time to store the values of A, B, and N, and off you go. So in this case, I did it a little bit differently. I stored the value of N and had a calculation for W. It's probably worth noting that N and W can swap places, so it doesn't matter which one you do. Depends on what you want to update. So teacher's choice. Okay, well, thank you very much for watching the webinar, everyone. And as I said, there will be materials that are there on the website. You can access that website at the link that you have there. And like I said, you can be contacting other people. Take a look at what's at the end of the activity sheets. So with no further ado, I will hand back to Emily.
Thank you for that, Roger. If anyone has any questions, now's the time to type it into the chat. As Roger mentioned, you will get access to the class activities that he's put together. You'll be emailed in a couple of days' time, most likely at the start of next week, with all of the information, including your PD certificate as well. There is also a link in the chat if you would like to register for any upcoming VCE curriculum webinars that we have. Just looking through the chat, make sure I haven't missed anything. Okay, I don't think we have any questions. So thank you, Roger, for that wonderful presentation, and for Peter's comments in the chat throughout. They were all very helpful. Thank you all for joining, and I hope everyone has a wonderful night.
Thank you.